Also, thank you for introduction. And so, hello everyone. So my name is Sasaki from MIT, and yeah, I'd like to thank all the people who are coming to this seminar, and it's a great honor that I can have some opportunity to give a talk here. So, yeah, it's my pleasure. Okay, so today I'd like to explain about using a mixed integer linear programming. I mean, how to automate the cryptanalysis against symmetric key. And in particular, I'd like to explain that application to meet in the middle attacks. Okay. Oh, you may realize this slide. But the interesting thing is, after the group round, then the top of the group G and the second of the group H will have a match, vice versa. And well, if I am quite lucky, then I can see a match between Belgium and Japan next week here. That's great. But in the worst case, Japan then goes with the product. So yeah, let's see now. Yeah, try it. But I think to win the tournament, the most important is after the first round of the tournament. So, anyway. Okay, so first I'd like to start from a recent trend in the symmetric crypto. Well, so there are like several hot topics in the symmetric crypto, and I'd like to focus on two of them. So one is COSIC Competition. So I think you have heard about it, but it's the competition to determine a portfolio of authenticated encryption. I mean, I don't explain what is authenticated encryption, but it's just like a designing competition. And it started from 2014, and the final round, I mean, 7 candidates were announced in March this year, so it's still a hot topic. And another is IoT. And IoT is always a buzzword to me. And so in the field of symmetric key, people always mention IoT to design lightweight crypto. And actually, so NIST will open the public code of lightweight symmetric key schemes soon this year. So, so what I want to say is a lot of designing activities in recent symmetric key crypto trend. Okay, so to design symmetric key schemes, so we have to check a lot of things. We may just modify some small part, and then it will impact to the security a lot. So we have to try a lot of certain parameters, and need to evaluate the security. So introducing automated tools is necessary. Otherwise, the work would be very hard. Okay, so there are two types of tools. So one is dedicated tools. For example, you may have heard about Matsui's differential or linear path search algorithm, which was developed around 1990. Or another is like path search algorithm for SHA-1 and SHA-2. This is really complicated. Or another approach is like generic tools. It's really generic, like search solver or MILP solver or constrained programming solver. This is a generic problems, not for crypto, not only for crypto. And I try to focus on the generic tools. And yeah, actually, generic tools are very actively discussed. And it's not about the reason why people are now like generic tools. And I can think of two reasons. So one is, so solvers are already optimized. So actually, the speed is quite fast. So it's useful. But besides, researchers can focus on cryptographic properties when we run generic tools. So we don't have to, researchers don't have to customize or optimize the solving speed. So that's quite nice. So another is easy to share the details of the model. So we have to convert the cryptographic program to to be understood by the tool. And this is really generic, so it's easy to share. And I think this is related to transparency of the designs, because previously I found one design that the designers claimed that security, they checked that the security was optimized already. But then I found that the research contained some mistakes, and actually in there it was not optimized. So design transparency is quite important, and so in that purpose, using generic tools would be fine. Okay, so goal of this talk is so I want to say that a lot of cryptanalysis can be automatically measured by using generic tools. So for example, so they can use to measure the security against differential cryptanalysis or linear cryptanalysis. Or similarly, impossible differential cryptanalysis or its counterpart, zero correlation attacks. It can also measure some higher order differentials like integral and cube attacks. Like all of those 6 attacks are differential based attacks. So in this talk, I'd like to explain the application to non-differential based attack, which is meet-in-the-middle attack. Okay, so first I'd like to explain mixed integer linear programming. Actually, I don't know why the people in symmetry call it mixed integer linear programming. The program is indeed integer programming, and it's often the form of 0-1 integer programming. And I explain those from the next slides. Okay, so this slide is basically for the linear programming. So the solution range is given by several inequalities. So this is a case for 2 variables. So everything can be drawn in the slides. And then the objective function is also defined as a function of with 2 variables. And the goal is to optimize an objective function, like minimize or maximize an objective function within the range defined by inequalities. Yeah, so this is linear programming, which can be solved efficiently. So in the integer programming, the solution must be integers. So the programming, the range is like a discrete system. It's not like a sequential system. So solving speed is much slower than linear programming. And so this is like a really conceptually sketch how it can be applied to crypto. And so we want to maximize the efficiency of the attack with this tool. And usually, so for the objective function, we define the number of active boxes. So basically, we want to minimize the number of active boxes. And the constraint is like a cutting off the invalid differential propagation patterns. So, yeah, so the solution is always like a valid differential pattern, and then to minimize the number of active boxes. You know, of course, like how to define the number of active boxes or like constraints is the main issue, but I just now skip those issues, and I later come back for the meet-in-the-middle attack. Yeah, and then the cryptographer's work is so defining those systems. And so after those systems are completed, we usually pass the system to some generic solvers, which some of them are in cost and some of them are for free, especially for academia. For example, the famous solver is like a Groby or Cplex or SCP. Okay, so I would like to introduce the 3 subset meet-in-the-middle attacks. So the first meet-in-the-middle attack in the literature appeared in 1977. This was by Diffie and Hellman. And one of the applications was meet-in-the-middle attack and WS, which is quite famous. And then the second one is the ancestor of the 3 subset meet-in-the-middle attacks. It was by Jum and Everts in 1985, It's against reduced round ds. So at that time, there is no word of 3 subset means the middle of duck, but actually the duck is in the 3 subset means the middle of ducks. And the name and like some evaluation for formula were recently formulated by Bob Nanoff and Rick Berger in 2011. And especially they proposed 3 subset means the middle of ducks against the specification of Canton cipher. So that's the overview. Okay, so let's get into the technical details. So this slide shows the block cipher. So you have block cipher E, which takes key K as input, or plain text as input, and that puts the corresponding subtext. Okay, so what is the generic approach to gather the key? And I think the only known approach is exhaustive search. And so if the key size is K, then the complexity is 2 to the K. Of course, there should be some like subtle details if the block size is smaller than the key size, but let's forget about such details. Okay, so then let's suppose this situation. So key consists of 2 parts, A1 and A2. And the first part of the block cipher is encrypted by A1, and the latter half is encrypted by A2. So then, the complexity of key recovery is 2 to the A1 plus 2 to the A2, so instead of 2 to the K. Why? So this is the basic means-middle attack procedure. So this is really basic, but so the attacker, so for all choices of A1, I mean the key for the first part, so compute the first half of the encryption algorithm, and so the results in the list L. So this part requires complexity of 2 to the A1. Then for each choice of A2, so the attacker computes decryption of the latter half, and then check if the value is stored in L. So if the guess is correct, then always the middle result will match. So you can get the knowledge of the correct key. And the complexity is the sum of 2 to the A1 and 2 to the A2. So this is the basic middle. But usually the ciphers can't be divided like this. So okay, so let's consider the case that the former half and the latter half contain some independent key bits, but also contain some shared key bits, so which is A0 in the slides. But still, the middle attack can be applied. Okay, so the procedure is, first the attacker gets all the possibilities of A0. Yeah. And then the latter thing is just simply meet in the middle. So the complexity is like 2 to the A0 times just like sum of 2 to the A1 plus 2 to the A2. So as long as the size of A1 and A2 is big, then the advantage is big. But even if A1 and A2 is 1 bit, then the attack is faster than the exhaustive search, at least by 1 bit. Okay, but the 3 subset means the middle attack can be more complex. So let's consider the situation that between the E1 and the E2, we have some middle rounds which involves all 3 subkeys, A0 and A1 and A2. Okay, so we want to match the results in the middle. But now we can't compute everything in the middle because in the forward computation we don't know the value of A2, or in the backward computation we don't know the value of A1. So it's impossible to fully compute and fully match the results. But in a typical block cipher design, the diffusion is imperfect only in one round, only in a small number of rounds. So let's, for example, you can consider phase-shift ciphers. So in one round, just like half of the cipher is updated. So even you don't know the key, you can compute the half of the state for one round. So by using such imperfect diffusion, you can partially compute the internal state for the middle round, and yeah, if you can partially match the results, then the meet in the middle attack works. Okay, so this is the partial matching, and the attack can be more advanced. So the second technique is called Streisand Cut. So now the difference is for in this figure, the forward part computes exactly from the plaintext, but in this slide, forward computation starts from the middle, and we have another independent blue part called like E2 bar at the beginning. For this situation, we still can apply the meet in the middle attack. Yeah. So the idea is, so we start from the border and boundary of the red part and the blue part. And in the blue part, we first compute the decryption to the plaintext. And after you get plaintext, then you make encryption queries to get the corresponding C. So like P and C are like physically located located away, but if you make queries, then you can get a connection of P and C. So you can regard that those blue part, two blue parts are in consecutive, and then the segment in the middle attack can work. Okay, so this is the Streisand Cut, and the last technique for the speed subset into the middle is called initial structure. So so in this slide, so the starting point, I mean the boundary of red part and the blue part are just in one state. But in this slide, so the boundary of E1 and E2 is not exactly the same. But yeah, so in the boundary of E1 and E2, we can also have some rounds that involves both of the A0 and the A1 and A2. Why it works? Because the diffusion, so we again use a property that the diffusion in a small number of rounds is not perfect. So as long as we can compute those rounds independently for red part and the blue part, then we can basically compute red part and the blue part independently, and so the meet in the middle that would work. Okay, so that's the brief overview of the three subset meet in the middle attack. So this is a summary. So what we need to apply the meet in the middle attack. So first, we need to find independent parts of E1 and E2, and sometimes E2 bar. But this depends on the key schedule. But some of the key schedule, this independent separation is very obvious, and I later show the case for gift block cipher. Now, another important thing is, so the advantage of the attack depends on the size of independent keywords. So we want to maximize the size of a minimum of A1 and A2. And to make the computation independent, we have to ensure that the computation in the initial structure is independent. And for the partial matching, yeah, we need to ensure that at least we can match the results from two directions for at least one bit. So that's the requirement for the three subset meet in the middle attack. Okay, so let's check the three subset meet in the middle attacks against gift. So first I'd like to show you the overview of the gift block cipher. So it's like present or like cipher. It's very lightweight. It was proposed at chess last year, and the block size is 64 bits, and the key size is 128 bits for smaller version of the gift. Okay, so the structure, the computation structure, I mean, you don't have to remember it, but the computation structure is, so first operation is application of 4-bit test box for any nibble, and then the bit is like swapped in some specified way, and then the key is XOR to the just like 32 bits of the state. I mean, of course, you don't have to remember and you don't have to follow the network. But the important thing which I want to emphasize is that the 128-bit key K is separated into 8 16 bits, 16-bit words, which is denoted by K0 to K7. And in each round, you use 32 bits of keys. So in the first round, K0 and K1 is used. And in the second round, K2 and K3 are used. In the third round, K4 and K5, and 4 rounds in K6, 7. And this is like iterated. So for this structure, you can see that like a subkey of subkey in which round is independent of subkey of another round. So the analysis is easy. So actually, in the design document, there is one 15-round meet in the middle, 3 subset meet in the middle attack. And so it's like a separation. So chunk means usually it's like a chunk of rounds, so we call it chunk. But so chunk separation is shown like that. So in the first 3 rounds, we don't see K6 and K7. It's obvious. And for the middle round, from round 7 to 9, we don't see K2 and K3. And again, in the last 3 rounds, we don't see K6 and K7. So we can have some independent keywords with this separation. And yeah, and then we have to do something for the 3-round insert structure and the 3-round partial matching. And actually, this is quite reasonable because it's obvious that independent chunks can be at most 3 rounds. I mean, if you go 4 rounds, then every key bits are used, so there should be no independent keys. So the remaining is to determine independent bits. So inside of the K2, K3, and K6 and K7, you don't have to use all of them as independent. So we have to determine which bits inside those keywords are independent. And we want to maximize the size of independent key bits to increase the attack efficiency. And we need to ensure the independence inside the insert structure, and we need to ensure the matching bits for partial match. Okay, so let's do it by using MILP. Okay. But first, I'd like to show some like example. So we have to construct the insert structure over 3 rounds of gift, and it looks like this. So in the first round, you see the key for the forward computation, and in the round 3, you see the key for the backward computation. Okay, so let's do some example. So this is bad example. So I just pick LSB of these keybits as the source of independent computation for blue word. And in the top, I chose just LSB of K6 as independent computation for the forward. And then I just trace the impact of flipping those 2 bits. But then in the right edge of the middle rounds, you can see that that bit is impacted from both of the forward computation and backward computation. So that means you can't simulate this the value of this bit independently of the other chunk. So, I mean, with this choice of the key bits, the attack doesn't work. Okay, so then let's take another good example. So in this example, I still use the same independent key bits for the backboard, but I changed the key bit for the forward computation in the first round. So it's now moved to the MSB. Okay, so then I just trace the impact, and yeah, it's independent. So actually it works, the insert structure works with this independent key bit choices. And then we also need to check the partial match effect. So during the partial match, the forward computation comes from the top. So before those 3 runs, you know all bits. I mean, the red part covers like all S boxes. But then after the key addition, because you don't know the MSB of the blue LSB of the blue part, and because due to the key schedule, the position is rotated, so it's not no longer than in LSB, but just you don't know the 1 bit of the key here. So in the forward computation, you can't compute the following S box because you don't know the bit value. And those 4 bits will impact to another 4 S boxes in another round. So you lose the information for 4 S boxes, but you still can compute other 12 S boxes. Then we do the same from the backward. From here to here, you know all the state values, which is colored by blue. But with this addition, you lose 1 key bit information in the state. And then after 1 round, so you can't compute this box. So in the backward computation, so you lose just 1 S box information, but you still can compute the other 15. So in the end, so you can match so 16 minus 5, so 11 S boxes. I mean, you can match like 44-bit information in the middle. So the meet in the middle works. Okay, so this is a summary of this example. So by choosing 1 MSB of the K6 and 1 LSB of K3, meet in the middle attack can work. So this is good information, but the complexity is very high because so we have to first guess any other dependent bits. So that's 126 bits. So it's already 2 to 126, and then the minimum of like 2 qubit size is added. So the complexity is 2 to 126. Okay, so now, so we want to maximize the size of independent qubits while the initial structure and the partial match are valid. Okay, so how to do it? So I want to do it in MILP. So we have to declare some variables, and we declare the following 64-bit binary variables, which is denoted by K2 sub 15 to K2 sub 0, and the same for K3 and K6 and K7. Okay, so we define that those variables take only when the corresponding qubit is used as independent qubits. So otherwise, those variables take 0. Okay, now, so we want to maximize the number of independent qubits. So the objective function is can be easily written like this. So the sum of the K2j plus K3j, I mean, just like the sum of the independent qubits, and the worst should be maximized. Yeah, but to balance the complexity, the number of active bits in the forward direction and backward directions must be balanced. So we need this constraint that sum of the independent qubits in the backward computation equals to the sum of the independent qubits in the forward computation. Okay, so this is the objective function, and then the remaining is just like a constraint to set up constraints to initial structure and constraints for partial match. And this is the constraint for partial match. It's just like give you the brief idea. So we also define another binary variables, which is called initial structure for 15 and initial structure for 14 till initial structure for 0. So we define those variables so that each takes 1 if the S box got impact during the forward computation. Okay, so let's back to this example. So it takes 1 if the S box is impacted from the forward computation. So that means for those 4 red S box, yeah, those are impacted from the independent qubits in the forward direction, so those take 1. And in the backward, we do the same. And for the fastest box is affected by the independent qubits in the backward computation. So only for the fastest box, the binary variables takes 1. Okay, so then this is a constraint. So we want to avoid the overlap. So the constraint is easy. Just like impact from the forward and plus impact from the backward is less than or equal to 1. I mean, if it's 2, then it's affected by both. So yeah, less than or equal to 1 is enough for all those boxes. But of course, we need to define some relationships between like a K6, 7 and the index for the active and the inactive of this box. And actually, this is the most complicated part, but I skip it because description of this part is exactly the same as the one in the differential attacks. So yeah, actually nothing is new is introduced to describe the relationships between K and the impact. But the idea here is that avoiding overlap can be modeled by inequalities. Okay, and then we do the same for the partial matching. So then in the figure in the figure on the right hand side, so the forward computation comes from the top, and you lose some information between due to the key addition. And after some rounds, still you want to check the internal state. And we introduce binary variables like partial match forward 15, partial match forward 14, and so on, and which takes 0 if this box can be computed without the knowledge of K2 and K3. So intuitively, we want a lot of zeros this time. And we do the same for backward computation. So again, let's get back to the example here. This is the example of the partial match. So for example, the fastest box in the forward computation can be computed without the knowledge of the blue part. So the fastest box takes 0. Or the fastest box can't be computed without knowing blue part, so it takes 1 in the forward direction. And yeah, we do this kind of analysis. Okay, so then the constraints is easy. So this time we want to know some values from both directions, and so the value 0 means we know the value. So the constraint is we know the value from the both. That means the partial match from the forward and the partial match from the backward. That means sum of those is 0 for some S box. Yeah, I mean, having just like one S box, that can be matched is enough. So I mean, equal to 0 doesn't have to be satisfied for all I. So this should be like for some I. And here again, we need to describe the relationship between K and the partial match state of the in the two directions. But this is also the same as differential attacks, so I just skip the details. And anyway, like knowing the value from the both state without key can be modeled by inequalities. Okay, so actually, I made the model and ran the tools to optimize the system. And so this slide shows the results. And the system contains 850 linear inequalities and 576 binary variables for the application to gift 15 round attack and gift. Actually, this is quite small. I mean, if you optimize, if you want to find some optimal differential trail in some cipher, then the system usually requires 100,000 inequalities or 10,000 variables. So compared to those big systems, the application to gift 64 is really small. So actually, I ran the Groby solver on the standard PC, and just like 1 second is enough to finish. But the result is good. As in the previous, the desired evaluation, so the sum of independent key bits in the forward direction is 8, and the backward direction is 8. But now the solver found that the sum of the independent key bits can be 16 in both directions. So this means the attack complexity, advantage increased from 2 to the 8 to 2 to the 16. So optimization actually works. Well, so this is just like the detected initial structure, and you can see that now like all S boxes are activated in either directions. So I'm pretty sure we can't go more than that. And so actually the tool returns the optimized solution. And so this is the case for partial match. So we lose a lot of information, but still we know the 16 bits information in the middle. Okay, so I'd like to conclude my talk. So the automated cryptanalysis with MILP, SAT, and constraint deprogramming is very actively discussed in the field of symmetric key. And this talk explains the application of MILP to like non-differential based cryptanalysis. And yeah, so actually as a result, we confirmed that 3 subset needed to be the attack and the gift 64 could be improved. And this is just like a first step. So future work would be like modeling chunk separation. So now I only modeled the maximization of free bits and initial structure and partial matching. But it would be nice if we can model the chunk separation such as well. And another is now I just consider I regard this box as black box. So if only 1 bit of the input is known, then I assume that all bits of the all output bits of this box is unknown. But maybe interesting to exploit the information inside this box. So those are future work. Yeah, that's about it. Thank you for your attention.